This is Math 1100, Practice Exam A. So what you need to know about these first 6 questions is they come from the entire unit, and there are 3 or 4 different rules of integration that could be used in this section, questions 1 through 6. So part of answering these questions is first deciding which rule applies, and then the second part obviously is actually evaluating the integral using the correct rule. So starting here in question 1, it's in the form of a quotient. We have a numerator and a denominator, obviously, but you notice there's a function inside of another function. That's usually a pretty good indication that this is going to be the general power rule with u substitution. So if you let the inside function equal u, we'll probably be able to use the general power rule in most cases when you have a function inside of a function. So if we let u equal that inside function 5x cubed minus 1, then du is 15x squared dx. So really the only issue that needs changing is we have the x squared dx here. This 30 just needs to be a 15. So we can move the 30 out front and multiply by a 15 there in front of the x squared. But remember, if you multiply by a 15 or multiply by anything out there, you've got to divide by that same value. So I'm going to divide by 15. And then there, 30 divided by 15 becomes 2. So let me write this over here. What this becomes is 2 times the integral of 15x squared over our inside function here. So what it looks like we have is this can change to du, 15x squared, dx, and then 5x cubed minus 1 is u to the third power. But I don't want to keep this as a fraction. I want to move this denominator up to the numerator. So when I write this in terms of u, I'm going to make this a negative exponent. So what I can write here is 2 times the integral of u to the negative 3 times du. So now if we apply the general power rule for integration, we're going to add 1 to the exponent, remember, and then divide by that value. So this becomes 2 times u. If we add 1 to negative 3, that gives us negative 2. Then we're going to divide by negative 2. This 2 and the negative 2 we're going to simplify to negative 1. So the u gets replaced then with 5x cubed minus 1 to the power of negative 2 plus c. And I'm fine if you keep it in that form. I mean, if you wanted to move the 5x cubed minus 1 back down to the denominator to give it a positive exponent, it would be negative 1 divided by 5x cubed minus 1 squared. Question 2, it's similar to question 1, and then in that it's in the form of a fraction. We have a numerator and a denominator, but there's no inside function. So it may not be that the general power rule applies, but we can still at least try u substitution, and maybe another rule applies. So if we let the denominator equal u, so x squared plus 2, then du, the derivative of that, is 2x dx. So you notice right off the bat, without really changing much, we have 2x dx, so this gets replaced with du, and then the denominator gets replaced with u. I'm going to go ahead and move this negative 1 in front of the integral sign. So the numerator again gets replaced with du, the denominator gets replaced with u, and hopefully this looks familiar. This is the integral rule for natural log. The integral of du over u is the natural log of the absolute value of u. So what we have is negative 1 times the natural log of the absolute value of u. So that's negative 1 times the natural log of the absolute value of x squared plus 2 plus c. Question 3. Now, we don't have really at this point a rule of integration that directly addresses natural log. Other than you may recall problems like this in the homework from section 6.1. 6.1 was integration by parts. So there's a pretty good chance this one is going to use integration by parts again, because there is no rule that directly addresses how to integrate natural log of x. So let's assume integration by parts will work here. So that means you need to choose u and dv. Now, the guideline, remember, for u is it needs to be something that's not only easy to differentiate, but when you do differentiate it, it becomes more simple than what it started with. And then the rule for dv is it needs to be something that's relatively easy to integrate. Now, the two parts of this product are square root of x and natural log of x. It would not work to use natural log of x as dv, again, because there is no real way to integrate natural log of x by itself. So then by default, natural log of x is going to become u, and then x to the 1/2 rather than the square root of x. X to the 1/2 dx is going to become dv. Now, then we need to find du. The derivative of natural log of x, remember, is 1 over x dx. We also need to find v. So dv has already been differentiated. So to go to v, remember, that's integration. So we need to find the antiderivative of x squared dx. That's just the power rule. So this is x. If you add 1 to the exponent, that becomes 3/2. And then if you divide by 3/2, that's the same thing as multiplying by 2/3. So there's v. And remember, the rule then for integrating this is u times v minus the integral of v times du. So we need u times v minus the integral of v. I'm going to go ahead and move the 2/3 in front. So this is v times du. Now I'm going to rewrite this again and clean this up a little bit. X to the 3/2 multiplied by 1 over x just means there's an x in the denominator. So again, just writing this out here, this part, what we have is x to the 3/2 divided by x to the first power. So what that means is you subtract exponents. 3/2 minus 1 is x to the 1/2. That's what happens there. So then this becomes natural log of x times 2/3 x to the 3/2 minus 2/3 times the integral now of x to the 1/2 dx. We've already integrated x to the 1/2. We did that right here. X to the 1/2 dx, the antiderivative is 2/3 x to the 3/2. So that's just going to replace this right there. So final answer. And this is where we replace integral of x to the 1/2. That was another 2/3 x to the 3/2. And then we would multiply those 2/3 multiplied by 2/3 together. Okay, question 4. First need to decide what the appropriate method of integration would be. We do have a function inside of another function here. So chances are we would use u substitution with the general power rule. Now, I'm going to let u equal that inside function, 5x squared plus 1. So then the derivative would be 10x dx. So that 20, I'm just going to move the 20 out here and then multiply it by the 10. So now we have a 10x dx. That's going to get replaced with du. And if we multiply by 10 there, we have to divide by 10 out in front. So what it turns into, 20 divided by 10 is 2, multiplied by the derivative. And then I'm going to change the square root to an exponent of 1/2. And then this, remember, is replaced with u. 5x squared plus 1 becomes u. So this is u to the power of 1/2. And then the 10x dx is going to get replaced with du. And then this is the general power rule. Okay, we have a base raised to an exponent, so we're just going to add 1 to the exponent and then divide by that. So this is 2 times u to the 3/2, and then either divide by 3/2 or multiply by 2/3. Okay, so that becomes 4/3, and then replace u with 5x squared plus 1 to the power of 3/2 plus c. Question 5, we have a base e exponential, so we may want to try first the rule that the integral of e to the u du is just e to the u. So if this is u, 2x squared plus 1, then du is 4x dx. Now we have 8x, so all we're off is just by the coefficient, which is fine. We have the variable correct with the correct exponent. We just need to change the coefficient, which we can do. If this had been x squared, or if this had been a different exponent than this, then we wouldn't have been able to use e to the u du. We would have probably had to use integration by parts, like in question 3. We can move the 8 out, multiply by 4 so that we have 4x dx, and then remember to divide by 4 there. So then this turns into 8 divided by 4 is 2. 2 times the integral e to the 2x squared plus 1 becomes e to the u, and then the 4x dx is going to get replaced with du. And then the rule that applies there is the antiderivative of e to the u is just e to the u. So this is 2 times e to the u, which equals 2 times e to the 2x squared plus 1 plus c. Okay, question 6. It's in the form of a rational expression. There isn't a function inside of a function, which usually indicates general power rule. Now, if it's in the form of a fraction where we have a numerator and a denominator, then oftentimes we can use the rule du over u. The antiderivative of du over u is natural log of u. If we do just a quick visual check, if we want this to equal u, so if u is equal to x squared minus x minus 12, then du would be 2x minus 1 dx. The problem now is there's no way we can change 2x into 2x minus 1, because remember, all you can do is multiply or divide by a coefficient. We can't just subtract a 1 right here. So there's no way we can make this into the form du over u, which would be the natural log rule. So that's not going to work. So then the other method would be partial fractions. This is what we learned in section 6.2 or lesson 6.2. So we need to take 2x over x squared minus x minus 12 and break it up into its partial fractions, and then find the antiderivative of each partial fraction. So you would factor the denominator into x minus 4, x plus 3. Since there's two factors there, we're going to have two partial fractions. And then after that, we multiply both sides by the lowest common denominator. So this would distribute to all three pieces there, which would leave 2x equals a times x plus 3 plus b multiplied by x minus 4. Now, if I want to solve for either a or b, that means I need to cancel one of the other variables. So if I want to solve for b, for example, I need to cancel a. And if I cancel a by letting x equal -3, minus -3 plus 3 is 0. 0 times a is 0, so a disappears. So I'm going to let x equal -3, then plug -3 in for all the x variables. That makes 2 times -3, -6. Here we have -3 plus 3, which is 0, so this part disappears. -3 minus 4 is -7. -7 times b is -7b. Divide by -7, we get b is equal to 6/7. Typically they come out to be whole numbers, but it's okay if it's a fraction. Now we also need to solve for a. In order to solve for a, we need to have b cancel. And if we let x equal -4, that's going to cancel b. So let's now let x equal 4. Plug 4 in for x. Here we get 8. Plug 4 here. 4 plus 3 is 7. 7 times a is 7a. Here, 4 minus 4 would be 0, so b disappears. Divide by 7, and a is equal to 8/7. So the partial fractions here, these become 8/7 over x minus 4, and then 6/7 over x plus 3. So those are the individual partial fractions that we can now integrate. So this turns into the integral of the first partial fraction, 8/7 over x minus 4. Now 8/7 I'm going to use as a coefficient here and just call it 1 over x minus 4. And then the second partial fraction, 6/7 over x plus 3, I'm going to move the 6/7 as a coefficient and call it 1 over x plus 3. These both need a dx. So now we have 1 dx over x minus 4. So this is in the form du over u, because if this is u, x minus 4, then the derivative is 1 dx. So we have du over u, and same thing over here. If this is u, x plus 3, then du is 1 dx. So this is also of the form du over u. And as you remember, the integral of du over u is natural log of the absolute value of u. So we have 8/7 multiplied by the natural log of the absolute value of x minus 4. And then we have 6/7 multiplied by the natural log of the absolute value of x plus 3 plus c. Question 7, this will be from section 5.4, definite integration and using the fundamental theorem of calculus. You find the antiderivative using any of the methods that we've learned in section 5.1, 5.2, 5.3, even 6.1, integration by parts. So we need to find the antiderivative of this. Now this is not a function inside of another function. There's no power here or square root or anything. So these are just individual terms that we can integrate separately, just using the power rule each time pretty much. So the antiderivative of that first term becomes negative x to the 4th over 4. The antiderivative of the second term is going to become x to the 3rd divided by 3, but then the 3 would cancel with that 3, so it just becomes x to the 3rd. And then the antiderivative of 3 is 3x. Now, the fundamental theorem of calculus says we're going to plug in the upper bound first, 3, into the entire antiderivative. So the antiderivative with a 3 plugged into it becomes the opposite of 3 to the 4th plus 3 cubed plus 3 times 3. That's the antiderivative with a 3 plugged into it. Then we subtract the value of the antiderivative with a -1 plugged in. Okay, so here 3 to the 4th is 81 multiplied by negative 1 is negative 81 fourths. 3 to the 3rd power is 27, and then 3 times 3 is 9. And then here, negative 1 to the 4th power is 1, but then multiplied by that negative is negative 1 fourth, plus negative 1 cubed is negative 1, plus negative 3. So this turns into 63 fourths, and the other one turns into negative 17 fourths. If we add those together, or subtract in this case, we're going to get 80 over 4, which is 20. Question 8 would be from section 5.5, area bounded by two curves. So the situation we have here, two parabolas. The first one, y equals x squared minus 8x plus 10, is facing like this. Negative x squared plus 4x minus 6 is facing upside down. So we're trying to find the area between. We need to find the intersection points so that we know the bounds of integration. Okay. So the way we find those intersection points is setting the two equations equal to each other. If x squared minus 8x plus 10 is equal to negative x squared plus 4x minus 6, get one side equal to 0, divide everything, factor out of 2, so then it factors into x minus 4, x minus 2, so we have 4 and 2 as our limits of integration. Now, we have a pretty good idea of, the next step is to figure out between x equals 2 and x equals 4, which one is the upper function and which one is the lower function. We have a pretty good idea just based on that crude drawing that we had, but the way to make sure is you choose a value between your bounds of integration and plug it into each function. So I'm going to choose x equals 3. So when x equals 3, here we have y equals negative 5. Here when x equals 3, we have y equals negative 3. So this has a lower value. Negative 5 is lower than negative 3, so this is the lower function. This is the upper function between those two values of x equals 2 and x equals 4. And that's important because now you set up your definite integration. So we have the integral from x equals 2 to 4. You start with your upper function and subtract the lower function. And if we combine like terms, we're going to have negative 2x squared plus 12x minus 16. So now at this point it's much like question 7. We're just finding the antiderivative and then using the fundamental theorem of calculus to plug in the upper and lower bound. And again, this is not a function inside of another function, so this is just integrating each term separately to find the antiderivative. So the first one is negative 2x to the 3rd over 3. This one's going to become x squared over 2. 12 divided by 2 makes it 6. So that's 6x squared, and then 16 becomes 16x. And then we apply the bounds of integration. So plug in the upper bound first. So that's going to become negative 2 times 4 cubed over 3 plus 6 times 4 squared minus 16 times 4. That's the antiderivative at the upper bound. Now we subtract the antiderivative at the lower bound, which is 2. Okay, so this is negative 128 thirds plus 96 minus 64. And here, we're going to have negative 16 thirds plus 24 minus 32. Okay, now that'll give us negative 32 thirds minus negative 40 thirds, which turns out to be 8 thirds. Okay, question 9 is an application problem from section 5.5, consumer and producer surplus. So you don't necessarily need to graph these, but we have a rough idea. 45 plus negative 3x, that's our demand function. So here's 45, we have a slope of negative 3, so it's going down. Then the supply function is 5 plus x, or x plus 5, so we have 5 and then a slope of positive 1. So equilibrium would happen right here. Okay? And if you remember from the discussion we had in 5.5, we need to find the x value and the price point of equilibrium. And then above it, up here, was the consumer surplus. That's the area above this horizontal line. And then producer surplus would be the area underneath that horizontal line right there. Now, since demand and supply functions are linear and is separated by this horizontal line, just makes two triangles. And we can find the area of each triangle using the area of a triangle formula, rather than area under a curve using fundamental theorem of calculus. But we need to find that equilibrium point. When two graphs like that intersect, then we solve a system of equations. So we set the equations equal to each other. Okay. So that gives us negative 4x equals negative 40. So x equals 10. So the value of equilibrium here is x equals 10. We just need the price value. So if we plug in 10 for either one of the equations, 10 plus 5 is 15. So price is 15. So this is 10. That's 15. So then for consumer surplus, we have a triangle that looks like this. So the difference between 15 and 45 is 30. So this is not drawn according to scale, obviously, and then from here to here is a horizontal distance of 10. So then the area is 1/2 base times height. So it's 5 times 30. Which is 150. Okay. So this is consumer surplus. For producer surplus, we have a triangle that looks like this. So that's 10, this length from here to here, and then the difference from 15 and 5 is also 10. So then the area would be 1/2 10 times 10, so that's 5 times 10, which is $50. And then here we have equilibrium. Okay, question number 10 would be from section 6.4, improper integral. And And we know it's an improper integral because one of the bounds of integration is infinity. So since the upper limit is infinity, we replace that upper limit with a variable and turn it into a limit problem. So the limit, I'm going to use b as b approaches infinity, and now we're going to go from 0 to b rather than from 0 to infinity of e to the negative 2x dx. So we need to find the antiderivative of e to the negative 2x. So we're going to use the e to the u rule. So if u is equal to negative 2x, then du is negative 2 dx. So we need to multiply by negative 2 so that we have the negative 2 dx, which means we multiply here by negative 1/2. So then we have negative 1/2, and then we have e to the u du. So then that's just negative 1/2 e to the negative 2x. That's our antiderivative. So if we evaluate that, negative 1/2 e to the negative 2x, from our bounds of integration 0 to b, we have negative 1/2 e to the negative 2b minus, so that's the antiderivative at the upper bound. Now we subtract at the lower bound, negative 1/2 e, negative 2 times 0 is 0. So then this becomes e to the 0, which is 1. 1 times negative 1/2 is negative 1/2. Negative 1/2, we have subtracted negative, so that's plus a 1/2 from that one. Okay, and then we are evaluating that as a limit as b approaches infinity. I'm going to rewrite this as limit as b approaches infinity, and then move the e to the negative 2b down to the denominator. So it's e to the positive 2b. Reason being is now we are replacing b with values that are approaching infinity, which means b is getting larger and larger and larger. Okay, so if you imagine b is 1, then 10, then 1,000,000, then 5 billion, we have e being raised to a power that's getting very, very large. So this denominator is getting very, very large, numerically speaking. The numerator stays 1, or negative 1, so we have negative 1 over a very large number. And if this number continues to get larger and larger, the overall value of this fraction actually diminishes and gets extremely small. And if this continues without bound or without end, then the value of this fraction is going to head towards 0. It's going to become so small and continue to head towards 0. And so what we have is we're able to evaluate this limit, even though we have infinity here. Because this value tends towards 0 as b approaches infinity, we treat it as 0. 0 plus 1/2 is 1/2, so we say it converges to 1/2.